VLDB this year, so this talk is sort of a preliminary version of that material. Okay, so this M3R is a re-implementation of the Hadoop API with sort of different performance characteristics. So Hadoop, if you're not aware of it, is a popular Java API for reduce programming. It's designed for out-of-core execution, and because it's writing a lot of data to disk, it's quite easy for it to be resilient, and allows it to scale up to 1,000 nodes. So this is the kind of the point in the design space that they're focused on. And it's quite a good sweet spot if you have large amounts of data, you need to be out-of-core, and so on. Underneath it is this HDFS, this distributed file system that it uses for storing all this data in a resilient fashion. And the HDFS will do the sharding and the replication transparently of all that data. So this is all a big chunk of open source code implementing this programming model. So M3R is a re-implementation of that API using X10, using managed X10. And because we're presenting the same API, we can run Hadoop applications on top of this instead, and just as sort of transparently getting those applications to work. We've reused some parts of Hadoop. We've reused HDFS and other things in order to interoperate with the existing HDFS stores, and also to avoid re-implementing things we don't need to. Because it's implemented on top of X10, it has different characteristics. So it's the execution is completely in memory. And that means you have to scale your problem size down to fit in your cluster RAM. And of course, because X10 is not resilient, that means these executions of these Hadoop jobs will not be resilient either, even if they would have been resilient in the original Hadoop. But if you have a small problem size and you have a small cluster where your nodes are less likely to fail, or rather a single node is less likely to fail, you can run considerably faster, closer to HPC speeds, because we're not doing all this extra stuff for resilience. So it's kind of like it's a different point in the design space, and it's a sweet spot, but it's covering a kind of a different domain. But the main point is that you can run Hadoop jobs unchanged on it. So if you, for example, can run your Hadoop job on a subset of your data, or you can test it on a subset of the data and get a much quicker turnaround time. So it's pretty useful. So an example of some of our performance numbers. We've run these applications. PageRank linear regression and global non-negative matrix factorization. And these are running on SystemML. So this is a sort of a programming environment for doing matrix algorithms. And at their core, all of these applications are sort of iterative matrix vector multiplications, sparse matrix times vector multiplications. So the standard SystemML implementation will convert these algorithms into Hadoop jobs and run them. And we can time them, and we're getting times in seconds here for each of these different sizes of these programs. But we can also run it on M3R, just using the same generated Hadoop jobs, and we get much faster times. So it's between, I think, 2x and 5x maybe, depending on the exact size and things. So the point is we're getting significant speed-ups without really changing the applications at all. But the downside is that we are limited to certain sizes. This is another test we run. These were code that we didn't change, we took from another project, but here we've written our own sparse matrix dense vector multiplication algorithm. And it's the same sort of iterative algorithm, so you can think of it as an abstraction of all of those algorithms, because it's sort of it's the main workhorse behind all of them. And by especially tailoring this algorithm for M3R, we can get even bigger speed-ups of about 50x or so. So in this graph here, we've got time on the y-axis and problem size down here. And this line is Hadoop, getting slower and slower as they go up, and then this line, which is hugging the x-axis, is our time on M3R for the same problem sizes, and this is a zoomed-in version of that graph because you can't really see the scaling. So the point of these slides is that we're getting considerable speed-ups for these same unchanged applications, essentially. So the usual way that you would run your Java Hadoop app is in your app, you'd use the API to submit multiple jobs into the Hadoop MapReduce engine. This is backed by the HDFS file system, and your data is there, and that would run happily. So what we've done is we have implemented our own engine in X10. Where's my mouse? There you go. So we've implemented our own engine, and it also uses HDFS, so it can access the same data and write its results out to share with Hadoop. And this is an X10 API, so the API itself is a bit different, and obviously it's a different language, so it's not really compatible at this point. But we can wrap it in using the Java interop layer. We can provide a Java API that looks exactly the same as the Hadoop API. And that's what allows us to just plug in standard Java Hadoop applications and just run them through this path and get different performance characteristics. And of course, you can also write applications directly to the M3R engine, but these are not going to be standard Hadoop apps, of course, they're going to be a different API. Okay, so the tricks we use to get these performance speedups are eliminating the resilience, eliminating the outer corners, and so on. So there's a lot of disk I/O that's disappearing. And also we try and optimize the network communication as much as possible for these matrix algorithms based on what we know from doing the same thing in the HPC space. And we're not just sort of, we're reducing disk I/O by using a cache, but we're not just caching the bytes, we're caching the actual objects. And that means we don't have to do serialization and deserialization as much. And that cuts down a significant amount of time as well. So let's go into more detail. So in these pictures, there are going to be some blue lines, which are slow communication paths, and black lines, which represent just copying a pointer somewhere. So we're going to be changing blue lines to black lines as we go from the Hadoop standard implementation through all the changes that we made to get to M3R as it is today. And we show all these various places that we've sped things up by doing this. So this is what an iterative Hadoop job would look like when running in Hadoop. So your data, your input lives on the file system to start with, and it comes in through this input. This is user code here that will deserialize it and turn it into objects that the mappers will then operate on. So the data is distributed to start with, so it's already fractured across multiple hosts and so on. And that will then cause the system to create multiple mappers, one for each partition of the data. So each chunk of that data will come in and be deserialized into input for the mapper. And the objects that it's being deserialized into are key value pairs. And the key and the type of the key and value is arbitrary. And the mapper can take those key value pairs, and each key value pair it receives, it can output a certain number, 0 or more, of other key value pairs that go into the next stage of the pipeline here, into the shuffle phase. So the mapper is sort of translating these input key value pairs into these other key value pairs. And the output types don't have to match the input types either. So the next stage, after the key value pairs have been emitted into the shuffle, is the reduced phase. And what happens in the shuffle is that there's a piece of user code called the partitioner which decides for each key which reducer it gets sent to, and therefore you're getting sort of a global sort going on. And then the reducer, therefore, each reducer will receive all of the values for a corresponding key, and it can then operate on all of that together in one go. So that's the sort of programming model. So the user is inserting little chunks of code into this system to operate on, say, an individual key in the mapper, an individual key value pair in the mapper, or all the values for a particular key in the reducer. And similarly, in the reducer, when you take all that in, you can produce a single key value pair, or many, or none, and they will be output serialized back to disk again. And if this is an iterative process, if you're doing multiple, doing a lot of multiplications in a row, then you'll read everything out of the disk again for the next job, and then you'll go through this whole process. So you can see that there's a lot of disk I/O and network I/O going on to facilitate this. Oh, I should say, when you go into the shuffle, what's actually happening is you're writing to disk for the shuffle, and then the reducers are using HTTP to pull that data over the network. So this is all because it needs to be out of core. So everything is streamed from disk to disk again, and so on. Okay. So in M3R is implemented on top of X10, and we do the shuffle communication using X10's ACT construct. So X10's ACT construct does not write anything to disk, so we immediately eliminated that disk I/O. But we've also immediately limited ourselves to in-memory data being shuffled around. The next thing is we have this cache. Now, because we're focusing on iterative jobs mainly, what we want to do is to be able to write stuff out of our reducer and have it stay in memory so that the next iteration can read it straight back out of memory again into the map job. So we want to avoid the serialization to disk, we want to avoid the actual disk I/O and the deserialization and so on. We're going to keep the actual objects around that are output by the reducer and then just alias them in the mapper again. So we're going to eliminate all of that computation using this cache object. And the way this works is that it pretends to be HDFS essentially. It's implementing the file system, and that's done using sort of distributed table using X10 concurrency and distribution constructs. So it's a fairly complicated piece of code to implement this cache that is keeping these objects around. Okay, now talking about network I/O, not just disk I/O. With a distributed file system, you can get some network I/O just because the data lives in a different place the way you need to fetch it. But it turns out standard Hadoop is pretty good at running the mapper in the right place, so it's local to the data. So Hadoop, as long as you don't have a node failure or you don't aggressively try and disrupt the system, you will probably not get very much network I/O out of the HDFS design in Hadoop. And of course, with M3R, we're using HDFS, so we get that for free. With the cache, we have the same kind of issues of because the cache is pretending to be a distributed file system. It has all of these same issues of where the data lives and where you're reading it from and writing it from. So, but we do exactly the same thing as Hadoop does. We try and run the map as local to the cache and proceed like that. So we managed to avoid all that potential overhead there as well, in the same way that Hadoop does. And so in terms of network I/O, that leaves only the shuffle phase to optimize. So what's really going on in the shuffle is you've got a number of mappers running on different machines, and each of them is emitting essentially arbitrary stuff, and they can emit things to various reducers depending on what keys they emit. So the key that you emit will be pushed through the partitioner object, which the user provides, and that will decide which reducer it goes to. So the key is kind of like the destination, the place where you're pushing it. Often the partition function is a hash code or something like that. So what we do in X10, or rather, what happens in Hadoop is that one mapper will be run in a single JVM and one reducer will be in a single JVM. So then there's no opportunity to really share memory between these two things at all. And all these JVMs are being started up and torn down all the time as well. So all of this adds overhead. But the main thing is that in X10, we start a JVM for each place, and that JVM stays there for the whole execution, which means all of the iterations, all of these Hadoop jobs. And in particular, if a reducer is running in the same place as the mapper, we can pass the alias straight across in the shuffle phase. So we don't have to do any network I/O there, or serialization or deserialization. The other point is that we're in a multi-core world, so we're going to run multiple mappers within the same place, and they're just going to use threads for activities rather than X10. So if you're emitting something from one mapper that goes to any reducers that are in the same place, then that can just be sent as an alias as well. And equally, if you send, this is where the semantics of X10 really start to become helpful. If you send for one mapper to 3 reducers, they're not local, but they're all in the same place remotely. What we do is we try and make the ats as big as possible. So we try and use as fewer at constructs and try and make them send as much as possible. And the effect of that is that you send less, because what at does, if you capture the same thing, the same variable or the same object 3 times in a single at, it doesn't get sent 3 times. The system will at runtime only send it 1 and then sort of leave a tag to it that it can use to represent the other 2. So you end up compressing this down to just 1 copy of that in the actual network protocol. So the result of that is that for free, using X10, when we send from one mapper to 3 different reducers in the same place, we get a reduction in the network bandwidth used. And this is also true for other mappers starting at the same place. So we're making these ats as big as possible, so we take all of the output from one place going to another place, we use one at, even if it's coming from multiple mappers to multiple reducers. Okay, so this is the example from earlier with the curved graphs. This is a code that we wrote implementing sparse matrix dense vector multiplication in an iterative style. So this means the matrix is being multiplied by the vector, and then the output of that is then multiplied by the matrix again, and you sort of converge, hopefully. And this is used in PageRank, in linear regression, and these other algorithms. So if you're in this sort of an HPC context, the way that you'd want to implement this algorithm efficiently is you'd probably partition your matrix, like so, into rows. So this is multiple rows here. This is a row block partitioning. So here we've got 4 places, and you start off with a partition vector, so that the first step would be to distribute the vector everywhere so that everyone has a copy of the whole vector. Of course, the vector is much smaller than the matrix. Even though the matrix is sparse, it's much smaller, so everyone can have a copy of the whole thing. And once you have that, then you can multiply all of your rows. Each place can individually do its rows with the whole vector and compute this square here. And because everybody's doing this, you then have your distributed vector, and that's in the same format that you started with. So that's the end of one iteration, and then you plumb that back into the beginning again, and you can keep doing this. So that's sort of at the high level, how you would implement this algorithm efficiently. And the key thing is, I mean, this is really obvious if you're not thinking about this from a Hadoop perspective, but you definitely want to only read G in once. The big matrix G, you want to read that once in at the beginning of the application, and then reuse it every iteration. You want to never communicate it, because you never need to. The only thing you do need to communicate is the little chunks of V which you have to distribute to everyone else so that everybody can have the whole vector so that you can do the multiplication step. And one extra complexity, if you were going to do this in Hadoop, you'd probably want to implement it in an out-of-core way. And the way that you do that is you'd also subdivide like this, so that the matrix is a 2D array of cells. And then each one of those you'd stream in and multiply it with the chunk of V that's appropriate, and then you'd form lots of these guys, which would have to be summed up in a certain way. So that's how you would do it in an out-of-core way. So now that we've got the sort of the high-level idea of what the algorithm should look like, we can talk about what it would look like in Hadoop. And there's various overheads that if you just run it in Hadoop, you would get, given the implementation of the programming model that exists in Hadoop. So the first thing you do is you read in your G and V matrix, your G matrix and your V vector, and this is distributed, so different mappers are running with different chunks of G and V. In order to multiply the right bit by the right bit, you have to push them through the shuffle phase and rewrite the keys of the vectors so that they are each cell of the matrix gets the right bit of the vector in order to multiply it by. So this means you have to push everything through the shuffle phase in order to align things so that within this programming model everything's in the right place and you can do the multiplication. And then your output of that, this is one job here because there's one shuffle, so the output of the job has to go back to HDFS, so that's outputting the whole thing to disk, including G. G gets pushed through the shuffle phase, but the V gets written to disk here. And then the next step, you have to sum up all these vector parts. So that's another job entirely. So you have to read in all your vector parts. You have to shuffle them so all of these parts go to the same reducer so that they can be added together in a bit of code. And then that output finally is the V that gets written back to HDFS. So you can see here there's a lot of disk I/O going along and a lot of communication that you wouldn't expect if you were to just think about this in an HPC context. Especially given what I said here, where the key to performance was to only read G once. So you can see G here. As you do, sorry, I forgot to mention, if you're doing this iteratively, every time you come around again, you're reading G again. So you're reading G off disk. G is the matrix, it's huge. You do that every iteration. And we're communicating G here in the shuffle phase at the top. And there's other communication going on down here as well. So what we're hoping is that by running this exact same program through M3R, given the changes that we've made and the sort of dynamic optimizations that we've done, all of this is going to disappear. Because although it exists in the programming model, we've sort of dynamically changed it into just copying pointers around. So if you take this picture and look at it with the cache in place, the cache is brilliant if you have an iterative algorithm because it means the output from the previous iteration stays in memory and then the next iteration we just pick it up from there. So what we've lost now is we don't see G being read each iteration because it comes out of the cache. The output from here just goes in here and the next job picks up for the cache and then the output from here goes into the cache. And then so iteratively you're just pulling things in and out of the cache each time and you only write through HDFS right at the beginning for the input of course and right at the end for the output. The next thing is the shuffle phase. We want to eliminate all of this extra communication going on. So at this point here, we want to, because of the programming model, we have to emit G into the shuffle phase so that it's visible in the reducer, so that we can actually compute with it. But we want to do this in a way that's free. We don't want it sent over the network or anything like that. This is also the point where the vector is replicated across all the places so everyone gets a copy of it. So we should see that little bit of communication for that, but we want to eliminate the G from this phase. And at the bottom we have only local work, because at each place we have a set of these vector parts that we want to add up into a single vector part, so there should be no communication there at all. So we want to see all of that disappear. Okay, so the fundamental thing that we give with M3R that Hadoop doesn't give you, that allows you to reduce all this communication away, is that we ensure that the reducer for a given partition number, what this means, the partition number, when you emit a key value pair from your mapper, you're pushing it into the shuffle phase. There's a partitioner object which will return the partition number for the key. So when this is telling it which partition to send each key value pair to, essentially. So this is the way in the programming model you choose a destination. And the additional thing that we give is we say that destination is always going to live in the same VM. And Hadoop doesn't give you this because it restarts the VM. It uses multiple VMs. It uses one for a reducer, and there's no opportunity for keeping that in memory. So, this in an iterative algorithm, this is very important because it means it's something that's emitted from a reducer will will be output into the cache, and then will come in again in the mapper in the same place because the mapper is run local to the data. And then if you try and transmit it to that reducer again, the reducer will be in the same place it was last time. So essentially, we're giving a way to make the memory, to make it clear which place each reducer is running at, and that allows you to target your shuffle towards a local reducer. So you're controlling the fact that it's going to be an alias there and not being sent over the network. So that's the key sort of concept here that allowed us to get that 50x performance. Because when we wrote this matrix vector multiplication algorithm, we wrote it in a way where we were essentially ensuring that everything that was sent through the shuffle phase that was remaining local would not be communicated. Capabilities or knowledge of these things. So the way we did this, we used X10 to build this fast core map reducer engine that used ATS. We reused a lot of the X10 semantics to do the communication, to do the distribution of data, and so on. And then we used the Java interop to wrap that in using Java code that presents the Hadoop API. So that's another crucial part of X10 that allowed us to do this. So doing all this, we avoided serialization, disk I/O and network I/O costs, and gave us 10x performance for unmodified Hadoop apps, and 50x improvement for this Hadoop app that we specifically designed, given our partition stability, given our given the guarantees that we provide for where stuff is going to run and the ability to send stuff locally, we got a 50x speed up for that specialized app. So that's it. Any questions?
You didn't modify the extended implementation one bit.
There is one small case. Let me try and you might know a bit about this too. So because we wanted to, so we're taking Hadoop objects. So Hadoop has its own serialization system. It does not use Java serialization.
Right.
It doesn't use, it uses its own writable and readables and all the rest of it. So what we wanted to do was not have to take those objects, destroy them, and turn them into extend objects so that we could do that without costing a lot of performance. So we did do a little tweak of the serialization system so that there's already an if statement in there saying if it's an X10 object, do X10 serialization. If it's a Java object, this is for interop, do Java serialization. So we just added a third case for Hadoop. And that was a very simple change, wasn't it?
Yeah, it was big. That's right. That's the one sheet. If it's a Hadoop writable, then use the Hadoop serialization.
I see like I was the one sheet.
But yeah, no language level changes, just
Right.
runtime.
So I think you mentioned that also like several optimization techniques, right? So then my question is, which part is contributed to the performance optimization, I think performance improvement? For example, then if you say like 15 times faster, right? So then there's lots of optimization, several optimization, the disk I/O animation or something like that. So then which part is contributing part?
Yeah, you're asking for a breakdown essentially.
Yeah.
I think it was quite difficult to even run this tool without. We were in a situation where if something was being shuffled and it should, if something was being communicated and it shouldn't have been. For example, if we were, because of some bug, communicating G, then we would simply run out of memory and it would crash because you would have this G landing on the system that already had the matrix there. We were really trying to run as big as possible. And so we would fill up the whole memory with this matrix. So then if we did have a problem, so we couldn't do a half system, if you like. We couldn't do half an I, because if we did that, we would just run out of memory. And we could have run it lower input sizes perhaps, but we didn't do that experiment. So I can't really give you an answer.
Thanks. So it's let me ask the questions. I think if you, so then I and other colleagues are using supercomputers like more that has more than 100 nodes, like more than 1,000 cores. I think your experiment just uses 20 nodes. So I think the problem that I'm just facing right now for this traffic simulation is that the communication layer is not very optimized in the Java and the managed X10. Especially the managed X10 uses Pocket Hotline, not using the M3R botnet. So for example, if you test this in M3R, like more than 100 nodes. I think I'm very curious about the performance scalability with a specific current specific function.
Yeah, we're probably not going to approach the performance of actual collectives anyway with this, because the Hadoop, it's so broad with what you can do in the shuffle phase, you end up with a really nasty collective to implement that doesn't allow much optimization. I just thought there. I think we should be able to run this on MPI if we were to get the MPI backend running with the managed backend. But then again, it would still be point-to-point communication being used with the shuffle as well. In terms of scaling M3R generally on a supercomputer, I mean, I think if you can run a JVM at each place on a supercomputer, which you can do that on BlueGQ, I assume. I don't know. If you can get a system which has a very large number of nodes, and where nodes don't go down very often, you should be able to run this on it and scale it up appropriately. But Hadoop, it might not be, because we're reusing parts of Hadoop, there's lots of threads going on, it might not be very supercomputer friendly to do that. So it's not, it would have to be an experiment that may not work.
And I think you'll lose some of you'll lose this optimization, right? As the numbers get bigger and bigger, the amount of aliasing you're going to be able to do is going to go down. So you might still get some things from the cache or from other things, but you'll lose some of this.
Well, the thing with all this stuff is that you shuffle everything. You shuffle your entire state. So in some sense, there will always be a very large proportion of it that you can optimize out by identifying what is actual communication and what is just the programming model forcing you to shuffle things.
Okay, thanks.
How about the memory consumption if you run the same application?
Good question. Well, obviously we're running up a much smaller cluster. It's kind of apples and oranges, really, isn't it? You would either have a large amount of input data and then you'd want to run it in Hadoop because you'd want to scale it up and have nodes failing left, right, and center, and then you'd be in a different world entirely. Or you're in this sort of small data, either you refined your data so you have less of it, and now you want to run it in this mode and have it be faster, or you're doing testing or whatever. So I don't think it's not very easy to make a comparison there, I think.
Can I say that the main speed up is because you use the memory for storage, right?
Yes.
For the M3R. So the shuffle stage is also be done in the memory, right?
Yes.
So
because we use X10 apps.
But the Hadoop shuffle stage writes the data into the persistent storage. Is also for the fault tolerance. So if a node crashed, and then the new map job can reduce the map data, right? So when how to handle the fault in your system?
We don't handle fault. If a node dies, then everything dies. That's the trade-off. So if you scale your application down so that you can run it on a smaller cluster, and the nodes, so that the chance of one node in the cluster failing is much less, then you would use our system, and then you'd have 50x more performance. So it's a different point in the space, really.
But many Hadoop applications do have a lot of fault. So
if you have 1,000 nodes, then it's quite likely that one of them will fail in the time between you start your application and when it finishes. But if you have fewer nodes, it's much less likely.
Okay. Second question: if the Hadoop also can use the memory for the storage, and if it uses the memory for storage, how many speed up can be achieved compared to this kind of Hadoop?
Are you referring to the ability to reuse JVMs? Hadoop has a mode where it will, instead of killing a JVM and then bringing a new JVM up to run, so if you go from a mapper to a producer, it will kill the JVM at the end of the mapper and then make a new JVM. There's a mode where it will reuse the JVM. Is that what you're talking about?
I mean that if the current Hadoop also use the storage, use the memory for storage, then
which storage?
Use the memory. Not writing to the HDFS, just like you.
Which version of Hadoop is this? Which version of Hadoop?
No. Just an assumption.
Hypothetical. If it
oh, if it is, sorry. Okay, carry on.
Right. So it's the speed up is also compared to this kind of Hadoop. I think it's maybe
you're
the
wondering
same.
if there might be some way of getting the best of both worlds by combining the two technologies, something like that, maybe? Yeah, I mean, what we've tried to do here is reuse X10 as much as possible. So if you were to do it in Hadoop, you'd probably have to re-implement a sizable chunk of what we've done in X10 in order to get this stuff happening. But I suppose it would be possible to just simply change Hadoop. If you imagine X10 did not exist and you did what we've done here, and you did it in Hadoop, and you somehow managed to get it to play nicely with the stuff that's already there, then you could potentially get these benefits, maybe.
You mentioned you implement the PageRank implementation. I want to know what is the largest data set you tested performance?
So this is 100,000 by 100,000 matrix. So we didn't implement PageRank. We used, SystemML is an IBM product, I guess, that already exists, and it had the PageRank implementation, which we just used without changing it, and we were able to. But it hasn't been sort of designed for M3R, so we were only able to push it up to about 400K. But when we did our own matrix vector multiplication, which is very similar to PageRank, we were able to push it out a bit bigger because we could optimize our in-memory representations and things like this.
For this purpose, for representative matrix, you use the GMM, the global matrix library of X10, or something?
That is kind of a parallel project, I guess.
Yeah, we didn't. We actually used another matrix library.
I see. What is the...
this is something we wrote just for this program.
Yeah, I mean, the thing that does it inside this, the implementation that you're seeing on the screen now is specific for Hadoop. So it talks about key value pairs in its matrix representation, and the key is a sort of a 2D index to represent which cell and which block cell and all the rest of it. So it has the Hadoop in it through and through. It's not like a reusable component that we just call.
Okay, thank you.
Okay, thank you again.